Here we are at the end of chapter 1, Algebra 1. We are down to the end, and this has been a bit of an exhausting chapter. We've had 9 sections, which is quite a lot, and some of the sections haven't agreed in terms of like one concept building on another, but we take it as it comes and we're going to deal with it. And this time, in this section 1-9, we're going to be dealing with statistics and analyzing data and using tables and graphs. Not too bad, kind of enjoyable. Our vocabulary is pretty short. The first concept we're going to talk about is the idea of a bar graph. And a bar graph, you've seen them before. They usually have bars, a little bit neater than what I'm discussing, where one side gives a category and the other side gives a quantity. And usually, bar graphs are sometimes called histograms, I believe. Histograms and frequency charts, something like that. So how often something occurs. So your numerical value will here, and the categories in which you're talking about will be across the bottom, will be your independent versus dependent variable. Yeah, you know. With bar graphs, we'll often be dealing with some sort of data or information. So in our case, our data would simply be information, generally of a numerical sort. All right. A circle graph will deal with percentages oftentimes, and it will be in a circle. And so we might say 50% of not people, because those aren't things, people love algebra. And over here, 20% sort of like algebra. And then we could say a small 10% really can't stand algebra. And let's say this is 30%. Looks more like 25 from my graph, but nope, can't be 25. Got to be add up to 100. I'm sorry, people. Let's say another 20%. Sorry for my unevenly made pies in the pie chart or the circle graph. 20% think algebra is super cool and loves it. I don't know, I just made that up, and I don't know if I made repetitive categories, but I do want you to see what one would look like before we start our text. And oftentimes it'll be color-coded, and it'll be beautiful, and you'll call your friends over to watch, and it'll be fabulous. Okay, so that's a circle graph. And then we have a line graph. And what line graphs often look like, it shows like change over time. So oftentimes this axis will simply be time, and this will be, this could be some of anything, number, frequency of something, and you'll see like a point here, a point here, a point here, then a point here, then maybe a point here, and then it might be, here's the trend over this amount of time for my business and how things have been going. And so there is your vocabulary: bar graph, data, circle graph, and line graph. So we're going to be dealing with all of those today. Let's get started with some very cool examples. So we're going to analyze a bar graph. The table shows the number of men and women participating in NCAA championship sports program back in the day in 1995 to 1999. And so we have a chart that shows this information. So here are the different categories, and then we have the different amounts. And actually in this particular bar graph, as you see down here, we will have two different colored bars representing different people, men and women, during different, let me show you the bottom portion, during different categories, or in this time, years. So the category down here that we're talking about will be years. The quantities will be the participants, and it's broken down into 2 bars such that we're dealing with men and women. So we've been asked to describe, in part A, we've been asked to describe the general trend shown in the graph. Well, we have 2 different trends, right? We see one trend for the men. They were up at about a little over 200,000, slightly below 200,000, just at slightly. So it looks like they're kind of staying pat at 200,000, whereas the ladies seem to be slowly but consistently increasing over the years in terms of their participation in NCAA sports. So that's exactly what I'm going to write. Men's participation has been relatively consistent, while women's participation has been steadily increasing. There. I think that's a good description. Let's take a look at the next portion of this problem. So here in part B, it says approximately how many more men than women participated in sports during the 1997 to 1998 school year. So I'll scroll right back up and I'll take a look at the 1997-1998 school year. I'll check out the approximate values. It looks like the men were at about 200,000. And the women were somewhere in the neighborhood of, I'm going to go with, this is 100, this is 150. This looks like it's just slightly above the middle. I would have said 125. I'm going to say 130. Now, when you have graphs like this and you are approximating the value and you're looking carefully, the best you can do is use deductive reasoning and say, all right, I know that this isn't perfectly marked, and I know I have to eyeball it, and this is like three-dimensional blocks and everything. So what we just did together is what I expect you to do for your work. So now that I've got those two values, I'm going to subtract them, getting 70,000 as the answer. Approximately how many more men? Approximately 70,000 men more competed than women. All right. And finally, what was the total participation among the men and the women in 1998 and 1999, in the 1998-1999 academic year? Again, go right back up to my chart. I need to eyeball these two values here. I need to make sure I know what's going on. So for this one, the amount of men, this being 250,000, this being 200,000, somewhere between here and there, I would say that I'm looking at about 210,000. Your answer might be different. You might say 212.5. I'm not upset about that. So I have 210,000. For the women, I'm getting really close to this 150 mark. I think that's about 140,000. And I'm going to use those answers to get the answer. And the sum is 350,000 people attended in that academic year. All right. So reading charts and reading tables can be as easy as that. Let's go ahead and look at this next one. So we're going to analyze a circle graph. And in a recent survey asked drivers in several cities across the United States if traffic in their area had gotten better or worse or had not changed in the past 5 years. The results of the survey are displayed in the circle graph. One good thing to do anytime you get a graph, take a look at all aspects of it so you know exactly what's happening. This is especially important in standardized testing. So, National Traffic Survey, we see a lot of people thought it was worse. Few people thought it was better. Some people thought it was the same, had not changed. And other people were not sure. They're like, I don't know. I don't drive. I don't know what's happening. All right. Or they did say drivers, so whatever. All right. So if we take a look at this one, if 450,000 people were surveyed, how many felt that traffic had improved in their area? Well, this is a great opportunity for us to re-examine how we handle percentages. And one way of handling percentages, well, I'll show you a couple ways. One way is to use the part over whole is equal to the percent over 100. This is probably my favorite just because I like it. It might not be your favorite, might not be the way you were taught when you learn percentages. Another way is to say, and it really does come out of this whole thing here. And when you solve this, you'd have to cross multiply. So you do whole times the percentage is equal to part over 100, and then you have to divide everything. And I'll show you what I mean. So you'd say part times 100 is equal to the whole times the percentage, okay? And then you would divide both sides by 100. I know this seems like a bit of gobbledygook. Just walk with me for a minute. And when you're done, you get that the part is equal to the whole times the percentage over 100. But if I do the percentage over 100, what I get is a decimal version, the decimal version of the percent. So this is also another very usable formula, and this is probably the one we'll use because most people like that. So what does this mean for our problem? So if I have 450, so I'm looking for a part of the of this situation of this 4,500 people. So the part I'm looking for, I'm going to write down part, right, is equal to the whole, which is 4,500 times the decimal version of the percent. Now, what percent am I concerned about is the question. How many people felt that traffic had improved in their area? So these people will be the better people. How do I write 8% as a decimal? If you remember, to go from percent to decimal, you move the decimal place over 2 spaces to your left, okay? And so we have 0.08 as that value. And when I multiply these two, and I get 360. And I didn't use a calculator to do this. I'm hoping you guys can do this without a calculator or super long multiplication, meaning take your 45, multiply it by 8, you get 360. That's not the end of the tail though, right? Because really this number is 0.0 and this is really 0 out here. So what you do is you now count the decimal points that you've added into the situation. So we've got, if I wanted to multiply 8 times 4,500, I put 2 zeros out here, but then this is an 8, this is 0.08, so then I've got to take the 2 zeros off, so I end up here. If that sounded like witchcraft, let me know. We'll talk about how to multiply numbers that are multiples of 10 in an easier way. So that's the answer, 360. Let's take a look at this next one. So if a city population was 647,000 is representative of those who are surveying, how many people could be expected to think that the traffic conditions are worse? Well, let's go back up and get the percent of people who think that it's worse. So we're looking at 63% thought that it was worse. All right, so we're talking about 63%. And this is now the whole. So the whole is going to be this amount here. So what was our formula again? If you don't remember, you can look at the last problem, or you can just check out what I'm doing here. The part is equal to the whole times the decimal version of the percent. And so continuing on, our part is equal to 647,000, lots of zeros, times the decimal version of 63%, 1, 2. So that's going to be 0.63. And we can multiply this, and when we do, we get 407,610. Here's one thing to make sure you know what you're doing. Let me just go back up here really quickly. Here, our whole was 4,500. And notice that 8% is a small number, right? Is a small amount in comparison to the 100%. So we expect our answer to come out to be a small amount in comparison to the whole. 8% is small to 100, and 360 is pretty small to 4,500. Similarly, 407,610 is pretty large in comparison to 647,000, right? And same thing with 63% in comparison to 100. So you can feel a certain amount of confidence about your answer. Let's take a look at another example, guys. Here we have a line graph in example 3, and we're going to analyze it. We'll talk about different things based on our graph. Take a look at your graph. What are we talking about? Higher education enrollment. We're looking at years and number of enrollment in the millions. So we were given some information. I want you to eyeball something down here. This little jagged part right here says this from 0 to the first value will not be consistent throughout, but everything else will. That's what this little jagged situation here is. All right, let's go. So estimate the change in enrollment between 1995 and 1999. So you would take 1995, find this value, 1999, find this value, subtract, and you get 0.7. Remember, this is in the millions, so 0.7 doesn't make sense. 0.7 millions makes more sense, but 0.7 million is really 700,000, which makes the most sense. Here we're going to predict the growth rate based on the growth rate between 2 years. So the growth rate between 1999 and 1998 was 0.3 million or 300,000. And so we're going to use that predict what would happen in 2005 if that growth rate continued from 1999. So if every year we gain 300,000, that's a 300,000 times 6, which gives us 1.8 million. If that happened from 1999, then we'd end up with 16.7 million students. Let's look at the rest in another